Hello everyone, today we are going to discuss a very important application of operational amplifier, that is instrumentation amplifier. By learning this lesson, you will be able to know how to understand the circuit diagram of instrumentation amplifier, what is the formula of gain, and how to solve the problem based on this topic, and why the instrumentation amplifier is called as data amplifier. So all these things we are going to discuss in this lesson. Let's start. So here we are going to discuss the very important application of operational amplifier, that is instrumentation amplifier. So instrumentation amplifier having the following certain characteristics parameter. The instrumentation amplifier which having the high gain, which having the high input impedance. So impedance means resistance. So we can say that which having the very high input resistance, which having the high common mode rejection ratio and low power consumption. So these are the certain characteristics of the instrumentation amplifier. An amplifier which having the high gain, DC coupled differential amplifier with single ended output, high input impedance, high common mode rejection ratio is called as instrumentation amplifier. So instrumentation amplifier is used to measure and control the physical conditions such as temperature, pressure, volume, humidity, etc. These parameters are very important in industries and consumer application purpose. So here, by using instrumentation amplifier, we will measure and control the temperature, pressure, volume, and humidity. So these parameters are very important. These physical conditions are very important for industries as well as consumer application purpose. So for example, in dairy and meat plant, so in industry, suppose dairy industry and meat plant, inside the temperature and humidity measurement are very important to maintain the product quality. So we want to maintain the product quality. For that purpose, we are using the instrumentation amplifier to maintain the quality of product. So block diagram of instrumentation amplifier is shown in figure A. So here, for input stage, we are measuring the physical quantity, that is pressure, temperature, volume, humidity. This is our input stage or first stage. Then this is the intermediate stage, and this is the output stage. So this input stage, there is transducer and preamplifier, and output stage there is the indicator or display. So here, so whatever the data we have took, that is measured, that is sensed by this using transducer, and then there are two preamplifier, and after it will transmit it to the intermediate state, and output stage it will display what is the reading regarding that for temperature, pressure, volume, humidity. So input stage, the transducer and two amplifier are used. So here the here is the transducer and two preamplifier are used. So transducer is a device to convert one form of energy into another form. So transducer we are using the transducer to convert the one form of energy into another form. It is used to according to type of physical quantity is being measured. Suppose for example we want to measure the pressure. So for pressure measurement purpose we want the different transducer. For temperature measurement we require the different type of transducer, and for volume and humidity purpose also we require the different type of transducers. So instrumentation amplifier amplify the low level output signal. So here the instrumentation amplifier which will amplify low level output signal of transducer at input stage, so that it can drive the indicator or display at the output stage. In this way, it is amplify the data. So the instrumentation amplifier is also called as data amplifier. So here In instrumentation amplifier, we have used the three operational amplifier, that is A1, A2 and A3. At non-inverting terminal of A1, we have applied the voltage V1, and similarly at non-inverting terminal of A2, we have applied the voltage V2. So here, according to virtual ground concept, Vp2 is equal to Vn2, that is V2. Similarly, Vn1 is equal to Vp1 is equal to V1. So whatever the voltage is came at non-inverting terminal here at this point, that is the V1. Similarly, at this point, that Vn2, that is equal to Vp2 or V2. So here V2. So here the current passing through this section is same. So we can say that IR3 is equal to IRG. So whatever the current is going in this side, that is the same current. So we know that the differential amplifier produce the output voltage. So output voltage V out, that is equal to R2 divided by R1 inside the bracket V2 minus V1. So this is our equation 1. And for op-amp A3, so for op-amp A3, the output voltage V out is equal to R2 divided by R1 inside the bracket VO2. This VO2 voltage is going in this way, and similarly VO1 voltage is going in this way. So we can say that VO is equal to R2 divided by R1 inside the bracket VO2 minus VO1. So this is our equation 2. So current passing through this branch is same. So that is the IR3 is equal to IRG. So this we have discussed in previous slide. So according to Ohm's law, V is directly proportional to the I, where R is the proportionality constant. So V is equal to IR. So VO2 minus VO1 is equal to IRG inside the bracket RG plus 2R3. So here already we have discussed Vn1. This Vn1 is equal to Vp1, that is V1, and similarly Vp2 is equal to Vn2, that is V2. So here we have seen that this voltage, that is VO2 minus VO1, is equal to the current passing through this, that is the IRG, and inside the bracket, that is the RG plus 2 times R3, 2 times R3. This is our equation 3. So here IRG is equal to V2 minus V1 divided by RG. So this is our equation 4. So here the current passing through this RG resistance, that is IRG. So according to Ohm's law, IRG is equal to the voltage at this point is V2, because V2 is equal to Vp2 is equal to Vn2. So voltage at this point is V2 and voltage at this point is V1. So IRG is equal to V2 minus V1 divided by RG. So this is our equation 4. Now equation 4 is putting in equation 3 V gate. So equation 4 is putting in equation 3, because here is the IRG. So this IRG value we have putting in this. So VO2 minus VO1 is equal to V2 minus V1 divided by RG inside the bracket RG plus 2 times R3. This is equation 5. So this equation 5 is putting in equation 2. Now the equation 5 is putting in equation 2, because here the VO2 minus VO1, here we want to put here. So V out is equal to R2 divided by R1 inside the bracket V2 minus V1 divided by RG inside the bracket RG plus 2R3. So this is our equation 6. We know that the differential mode gain of operational amplifier, that differential mode gain of operational amplifier is A is equal to V out divided by V2 minus V1. So here also this we can write V out is equal to A V2 minus V1. So here suppose we have compared the equation 7 and 6. So we have get that here is the V2 minus V1 is common thing here, and remaining all these are the which is related to the A. So comparing equation 6 and 7, we get A is equal to R2 divided by R1 RZ plus 2 R3 divided by RZ. So this is we get the gain. So A is the differential mode gain, or A is equal to R2 divided by R1, because here is the RZ, here is also the RZ. We can write 1 plus 2 R3 divided by RZ. So here this gain is totally depends on resistance R1, R2, R3 and RZ. So this is the our final equation of gain, and on the basis of this equation we will solve the problems. So here we are going to discuss the problem based on this instrumentation amplifier. So this formula we have seen that this is the differential mode gain, that is the R2 divided by R1, 1 plus R2 times R3 divided by RZ. So in first problem, in above figure, RZ is equal to 1 kilo ohm, R3 is equal to 100 kilo ohm, and R1 and R2 is equal to 10 kilo ohm. Find the differential voltage gain of the instrumentation amplifier. So here in this equation we have given RZ is equal to 1 kilo ohm, R1, R2 is equal to 10 kilo ohm, R3 is equal to 100 kilo ohm, and we want to identify the differential voltage gain. So this is the formula of differential voltage gain. So this we can write this or in this way. So here R2 is equal to 10 kilo ohm, R1 is equal to 10 kilo ohm, RB is equal to 100 kilo ohm multiplied by this 2, and RZ is equal to 1 kilo ohm. So this kilo get cancelled. So 100 multiplied by 2, that is 200. So 200 plus 1. So gain is 201. So this is our gain is 201. So this is our required answer. Problem second, in figure B, if RZ is equal to 1 kilo ohm, R3 is equal to 99 kilo ohm, R1 is equal to 10 kilo ohm, and R2 is equal to 20 kilo ohm, what is the output voltage if the V in is equal to 2 millivolt? So here we want to identify the output voltage. So here we want to identify the output voltage, but we are familiar with that the differential mode gain. So differential mode gain is A is equal to R2 divided by R1 inside the bracket 1 plus 2 RB divided by RZ. So R2 is equal to this 20 kilo ohm and R1 is equal to 10 kilo ohm. So this kilo get cancelled. Similarly, this RB is 99 kilo ohm and RZ is equal to 1 kilo ohm. This kilo get cancelled. So this 99 multiplied by 2, that is 198 plus 1, and here 20 divided by 10, that is 2. So 2 inside the bracket 1 plus 198. So 2 inside the bracket 199. So 199 multiplied by 2. So A is equal to 398. But we are familiar with that the general formula of the gain. Gain is equal to V out upon V in. So here in this we will get the gain. So we have given the V in. V in is the 2 millivolt. So V out. So V out is equal to this V in multiplied by gain. So this V in is the 2 millivolt. So 2 million is 10 to the power minus 3 multiplied by this gain 398. So V out is equal to 0.796 volt. If you like this lesson, please like, comments and subscribe this channel. Thank you for watching this video. Thank you very much.